Smart grids are modernized electrical distribution networks utilizing technology for improved efficiency and reliability. The features include advanced metering infrastructure, also known as AMI, distributed generation, and real-time monitoring. Microgrids are small-scale, self-sufficient power systems that can operate independently from the main grid. The benefits include resilience during power outages and potential cost savings. Integrating smart grids and microgrids can offer potential benefits. Microgrids can act as distributed energy sources and enhance grid stability. Implementing smart grids and microgrids faces challenges such as cost and regulatory barriers. Opportunities exist for economic growth, job creation, and improved energy security. Smart grids and microgrids offer insights into the future of electricity delivery, relevant to anyone interested in energy innovation, the latest advancements in electrical grid technology, sustainability, the potential for microgrids to reduce reliance on fossil fuels, resilience, and the use of microgrids to ensure uninterrupted power during emergencies. The economic potential of the smart grid and microgrid industries is significant. Considering smart grids, their reliance on advanced metering infrastructure offers several advantages. Firstly, AMI enables real-time monitoring of energy consumption patterns. This allows utilities to better understand demand and optimize power generation and distribution accordingly. Secondly, AMI facilitates dynamic pricing where electricity rates vary based on time of use. This incentivizes consumers to shift their energy usage to off-peak hours, reducing strain on the grid during peak demand periods. Thirdly, AMI supports remote meter reading and diagnostics, eliminating the need for manual meter readings and enabling quicker detection of outages and other grid issues. Distributed generation, another key feature of smart grids, involves generating electricity closer to the point of consumption. This can take various forms, including solar panels, wind turbines, and combined heat and power systems. Distributed generation offers several benefits. Firstly, it reduces transmission losses, as electricity does not have to travel long distances from centralized power plants. Secondly, it enhances grid resilience by providing backup power during outages. Thirdly, it promotes the use of renewable energy sources, contributing to a cleaner and more sustainable energy future. Real-time monitoring is crucial for the efficient and reliable operation of smart grids. It involves using sensors and data analytics to continuously monitor the status of the grid and detect any anomalies or potential problems. Real-time monitoring enables utilities to respond quickly to grid disturbances, prevent outages, and optimize grid performance. Microgrids, operating independently from the main grid, offer a number of advantages. 1. They enhance resilience during power outages. When the main grid fails, microgrids can continue to provide power to critical facilities such as hospitals, emergency services, and data centers. 2. They offer potential cost savings. Microgrids can generate electricity more efficiently than the main grid, especially when using renewable energy sources. 3. They can improve power quality by providing a stable and reliable source of electricity. The integration of smart grids and microgrids can create a more flexible and resilient electricity system. Microgrids can act as distributed energy sources, providing power to the grid during peak demand periods. They can also enhance grid stability by providing ancillary services such as voltage regulation and frequency control. The successful implementation of smart grids and microgrids requires addressing several challenges. The high cost of deploying these technologies can be a barrier to adoption, especially for smaller utilities and communities. Regulatory barriers can also hinder the development of smart grids and microgrids. Existing regulations may not be well suited to these new technologies, and it may be necessary to update regulations to facilitate their deployment. Despite these challenges, smart grids and microgrids offer significant opportunities for economic growth, job creation, and improved energy security. Investing in these technologies can create new jobs in manufacturing, installation, and maintenance. It can also attract new businesses and industries to communities. Furthermore, smart grids and microgrids can enhance energy security, by reducing reliance on imported fossil fuels. For those interested in the future of electricity delivery, the advancements in electrical grid technology are important. Smart grids and microgrids represent a significant step forward in the evolution of the electricity system. They offer the potential to create a more efficient, reliable, and sustainable energy future. The role of microgrids in promoting sustainability is particularly noteworthy. By enabling the integration of renewable energy sources, microgrids can help reduce reliance on fossil fuels and lower carbon emissions. Microgrids can also improve energy efficiency by capturing and reusing waste heat. The ability of microgrids to ensure uninterrupted power during emergencies is a critical benefit. In the aftermath of natural disasters or other emergencies, microgrids can provide power to essential services, helping communities recover more quickly. The economic potential of the smart grid and microgrid industries is substantial. As these technologies become more widespread, they will create new markets and investment opportunities. Companies that develop, manufacture, and deploy smart grid and microgrid technologies will be well positioned to benefit from this growth. Considering the technical aspects, smart grids often employ sophisticated communication networks to enable real-time data exchange between various grid components. These networks utilize a variety of communication protocols, including fiber optic cables, wireless technologies, and power line carrier communication. The data collected from these networks is used to monitor grid performance, detect anomalies, and optimize grid operations. Microgrids typically consist of a combination of distributed generation sources, energy storage systems, and load controllers. The distributed generation sources can include solar panels, wind turbines, fuel cells, and combined heat and power systems. The energy storage systems can include batteries, flywheels, and pumped hydro storage. The load controllers are used to manage the flow of electricity within the microgrid and to ensure that the loads are met. From a regulatory perspective, the development of smart grids and microgrids is often influenced by government policies and regulations. These policies and regulations can provide incentives for the deployment of these technologies, such as tax credits and grants. They can also establish standards for grid interconnection and operation. The integration of renewable energy sources into smart grids and microgrids presents some unique challenges. Renewable energy sources, such as solar and wind, are intermittent, meaning that their output varies depending on weather conditions. This intermittency can create challenges for grid operators, who must ensure that the grid remains stable and reliable. To address this challenge, smart grids and microgrids often incorporate energy storage systems to buffer the variability of renewable energy sources. Additionally, advanced control algorithms are used to manage the flow of electricity from renewable energy sources and to coordinate their operation with other grid components. The use of advanced metering infrastructure in smart grids raises some privacy concerns. AMI systems collect detailed data on energy consumption patterns, which could potentially be used to infer information about consumers' activities and habits. To address these concerns, utilities are implementing privacy safeguards such as data encryption and anonymization to protect consumer data. The deployment of smart grids and microgrids requires a skilled workforce. Workers are needed to install, maintain, and operate these technologies. Educational institutions and training programs are developing curricula to prepare workers for these jobs. The development of smart grids and microgrids is an ongoing process. Researchers and engineers are continuously working to improve the performance and reliability of these technologies and to reduce their cost. Future innovations are likely to focus on areas such as advanced control algorithms, energy storage technologies, and cybersecurity. The potential benefits of smart grids and microgrids extend beyond the electricity sector. These technologies can also contribute to other societal goals, such as reducing greenhouse gas emissions, improving air quality, and creating jobs. As the world transitions to a cleaner and more sustainable energy future, smart grids and microgrids will play an increasingly important role. The economic factors driving the adoption of smart grids and microgrids include the declining cost of renewable energy technologies, the increasing cost of fossil fuels, and the growing demand for electricity. Government policies and regulations also play a significant role in shaping the market for these technologies. The technical standards that govern the interconnection and operation of smart grids and microgrids are constantly evolving. These standards are developed by organizations such as the Institute of Electrical and Electronics Engineers, also known as IEE, and the International Electrotechnical Commission, also known as IEC. The cybersecurity of smart grids and microgrids is a critical concern. These systems are vulnerable to cyber attacks that could disrupt grid operations and compromise sensitive data. Utilities are implementing cybersecurity measures to protect their systems from these threats. The social and environmental impacts of smart grids and microgrids are generally positive. These technologies can help reduce greenhouse gas emissions, improve air quality, and create jobs. However, there are also some potential negative impacts, such as the visual impact of wind turbines and solar panels. The long-term sustainability of smart grids and microgrids depends on factors such as the availability of renewable energy resources, the cost of energy storage, and the effectiveness of government policies. These factors will determine the extent to which these technologies can contribute to a cleaner and more sustainable energy future. The scalability of smart grids and microgrids is an important consideration. These technologies must be able to scale to meet the growing demand for electricity and to accommodate the increasing penetration of renewable energy resources. The interoperability of different smart grid and microgrid components is essential for ensuring that these systems can function effectively. Standards and protocols are being developed to promote interoperability. The resilience of smart grids and microgrids is a key factor in their ability to withstand disruptions such as natural disasters and cyber attacks. Redundancy and backup systems are used to enhance resilience. The affordability of smart grids and microgrids is important for ensuring that these technologies are accessible to all consumers. Government subsidies and financial incentives can help reduce the cost of these technologies. The public acceptance of smart grids and microgrids is crucial for their successful deployment. Public education and outreach programs can help raise awareness of the benefits of these technologies and address any concerns. The integration of electric vehicles into smart grids presents both challenges and opportunities. Electric vehicles can increase the demand for electricity, but they can also be used as energy storage devices to help stabilize the grid. The use of data analytics in smart grids is enabling utilities to improve grid operations, reduce costs, and enhance customer service. Data analytics can be used to predict demand, detect anomalies, and optimize grid performance. The role of artificial intelligence in smart grids is growing. Artificial intelligence can be used to automate grid operations, improve cybersecurity, and enhance customer engagement. The regulatory landscape for smart grids and microgrids is constantly evolving. Governments are working to create regulatory frameworks that support the deployment of these technologies while protecting consumers and ensuring grid reliability. The financing of smart grid and microgrid projects can be challenging. Traditional financing models may not be well suited to these projects, and new financing mechanisms are being developed. The workforce development needs for smart grids and microgrids are significant. Educational institutions and training programs are working to prepare workers for the jobs of the future. The international collaboration on smart grids and microgrids is helping to accelerate the development and deployment of these technologies. Countries are sharing best practices and collaborating on research and development projects. The future of electricity delivery is likely to be characterized by a more decentralized, resilient, and sustainable energy system. Smart grids and microgrids will play a central role in this transformation. The increasing adoption of smart home technologies is creating new opportunities for integrating smart grids and microgrids with residential energy systems. Smart home devices can be used to control energy consumption, manage demand response programs, and provide data to utilities. The development of new energy storage technologies is crucial for the widespread adoption of smart grids and microgrids. Batteries, flywheels, and other energy storage technologies can help to address the intermittency of renewable energy sources and improve grid stability. The use of blockchain technology in smart grids is being explored. Blockchain can be used to create a secure and transparent platform for energy trading and to manage distributed energy resources. The integration of smart grids with other infrastructure systems, such as transportation and water, is creating new opportunities for improving efficiency and resilience. For example, smart grids can be used to coordinate the charging of electric vehicles and to manage water resources. The importance of cybersecurity in smart grids cannot be overstated. These systems are critical infrastructure, and a successful cyber attack could have devastating consequences. Utilities are investing heavily in cybersecurity measures to protect their systems from these threats. The role of the consumer in smart grids is evolving. Consumers are becoming more active participants in the energy system, using smart home devices to control their energy consumption and participating in demand response programs. The data privacy implications of smart grids are a growing concern. Utilities are implementing data privacy safeguards to protect consumer data. The environmental justice implications of smart grids are also being considered. Efforts are being made to ensure that the benefits of smart grids are shared equitably across all communities. The long-term vision for smart grids is a fully integrated, intelligent energy system that is capable of meeting the energy needs of society in a sustainable and reliable manner.